8.11. Okay, so let me go over the discuss the problem 11 first. So this is a question. Find the exact length of the curve. The curve is actually is given by the function. It's going to be x cubed here divided by 3 plus 1 over 4x, and the x is between 1 and 2. I may skip some steps. Okay, that's the idea. Is very simple. You write down the length function. Okay, the length is going to be the integral from L to S, right? That's the original formula. Then you choose x variable or y variable. I think clearly this will be the x variable because the y is given as a function of x. So x is between 1 and 2. All I have to do is just find the derivative, then simplify the expression and the radical. So that will be x squared, and that would be negative. Right? Yeah. So the derivative will be x squared plus negative. Okay. This is going to be negative 1 over 4x squared. Then you should know that you're going to get rid of the radical. You should write, trying to express the function inside radical as a square of some function. Right? So you will get 1 plus x to the 4th power. And when you multiply this out, there will be 1 half, and plus 1, this is a square. Okay? Then you realize that this is negative 1 half, but it combined with 1. It's become positive 1 half. So it's it's going to be x to the 4th plus positive 1 half. Right? Then you should see that this is going to be square of some similar function, x squared, instead of minus and plus. So it'll be x squared minus plus a quarter of x, 1 over x squared. Okay, then you can get rid of the radical. Okay. So you will get x squared plus a quarter of x squared dx. Then next step is just find the antiderivative of the function. Then you're done. Okay. That's the key part, right? So antiderivative of this function will be like 1/3 of x cubed. The other way is 1/4, right? X to the negative 2. So the antiderivative is negative, 1/4 x to the negative 1. When you differentiate, you get that point. So evaluate that to end point. Okay. All right, so let me finish that. It's 2 cubed minus quarter times negative to the negative 1, and minus 1/3 minus a quarter. Okay. So that is the answer to the problem. Now, what we're going to do today is going to find the area of a surface of a revolution. But this is this is supposed to be the topic in Math 261. But since the surface, we're talking about surface of revolution, so we end up with a single integral single function. So that's what we can discuss here. Now, what we needed to know is the following factor first. Okay, here's a section 8.2. It's about area of a surface of revolution. Okay. The simplest one will be the cone, portion of the cone. So let's take a look at the simplest one first. So this is a cone. Okay. So I only consider this portion of the cone. Now, what is the formula for the surface area of that part? Because this cone is a very special surface of revolution. Okay, so we using elementary mathematics, we can figure it out if this is the L, okay, and this is radius 1, and that's radius 2. Okay. Well, we can find the formula is given in the book. I'm not going to spend time to derive the formula. What we get here is going to be the area is going to be 2 pi, and the average value, this is R, right? Here's R. Here, 2 pi RL. And what is R? R is the average value of this 2. Okay. That's it. So this is a formula we're going to use to derive the area formula for a surface of a general surface of revolution. Right? The idea is simple. So we have we have a curve. Yeah, this is an axis, right? And I have a curve in the space. So this curve we can measure the length, right? Whatever, right? So the arc length will be, will be S, okay, from here to here. So if you rotate around this axis, what I'm going to do is I'm going to divide this surface of revolution into many slices. So how can I, yeah, so this is one slice, one tiny slice. Right, I'm going to color. So the area of this tiny slice, I call it dA, right? That's the surface area. So I'm going to estimate. See, but this piece looks like a piece like that, you know. This is going to be approximated by the cone, right? So if you take a tangent, if you draw the, this is a tangent line, right? So this will be the ds, the arc length, kind of changing the arc length. Then the radius, if here's r, okay, is the middle point. So this is going to be approximated by 2 pi r times L. L is ds, okay? So the tiny change, this slide, the area is about dA equals 2 pi r ds. R is the radius of that slide. The radius, you know, you have two circles there. So this is going to be the average value of these two circles. Average value of these two radius. Right? So now you can imagine the total surface area is going to be the integral of yeah. Okay, add all those tiny bit area together. Right? But this integral is going to be just integral 2 pi r ds. Okay? And then it depends. If the length is from here, s equals 0, that's s equals L, then it's from 0 to L, okay? Now here, there's R there. R depends on S. Okay, if you are able to express R in terms of S, then you don't need to use X, Y variable, right? There's no need to use X, Y variable. If you can determine the radius of that circle at the location of R, S, and R depends on S, right? When S changes, then R changes. Okay, if you can find the formula for r in terms of s, then you just evaluate this integral with respect to s. But in reality is that it's almost impossible to find the arc length of the curve. Okay, so this axis could be the x-axis, could be y-axis, could be any vertical line. So let's do some exercise. I'm not going to give you a very specific formula here, but if you are able to, yeah, you can replace ds, right? ds is usually going to be dx squared plus dy squared. This can be taken out 1 plus dy over dx. Okay, this also can be changed to dx squared dy plus 1 dy. Okay, in either form. Even you can parameterize this curve using using another parameter. Then this will be x prime t squared plus y prime t squared and dt. Okay. All right, so that's it about this whole idea. Now, the next, we're going to discuss some example. Okay, most of cases are just a set of integral to for the surface area. Right. So the first example I want to discuss is, right. So this arc, right. Parabola x it's going to be y equals x squared, and this is going to be from the point 1, 0, 2, 2 and 4. Right. This is going to be rotated about the y-axis. Right. So find the area of the resulting surface. So for step 1, first of all, you are in the xy coordinate system, right? It's 2-dimensional. Y equals x squared. Y equals x squared, and when x equals 1, from 1 to 1, yeah. So this is a parabola. Right, that's a piece. Here's the 1 and the 1. Here's 2 and the 4. Okay, this is just portion of the parabola. So you're going to rotate it about the y-axis. Okay. I want to know the surface area. How do you solve this problem? Well, this is the original curve, right? This is the original curve. Right. This curve I have arc length. So ds is this part. Right? So this surface is going to be the area of this portion is going to be approximated by the similar portion in the cone. Okay, so if the radius here is r, right, then dA is going to be 2 pi r ds. Okay, so you have to draw the picture. What is r? What is ds? So that is the area of this one slice, and add them together, you get the total area. Okay. So how can I solve the problem? I change it to the integral of one single variable. Right? So for an arbitrary point here, x and y, right? You have to learn this idea, otherwise you're not going to make it. Okay, cannot set up the integral. Don't by guessing trying. But you have to understand how do you set up the integral. Okay, so the area is going to is the integral of dx, okay, which is going to be 2 pi r ds. Okay, that's the original formula. The next part is whether you're going to use the x variable or use a y variable to evaluate this this single integral. So you take a point x and y on the original curve. You have to draw the graph, okay? Now, if you don't draw the graph, it doesn't mean you understand it. Just memorize some special formula without understanding the formula in the book, okay? So you draw the graph, you take a point on the original curve with coordinate x and y. You write down what is r. R is going to be x, right? For that particular point. R is x, right? And the y depends on x, right? So y depends on x squared. It's going to be x squared. Yeah, this is not the easy part. If I put they always have some confused, and what I'm going to do, have no clue. You have to draw the picture. Step 1, draw the picture. You have to, step 2, you mark, yes, indicate radius r and the point on the original curve. Then you have to see what you have to do, right? So now it sounds like you're going to use x variable here, right? So x is between 1 and 2, right? So I decided to use x. You can use the y variable, no problem, okay? It's 2 integrals. It's not necessary to use x variable in this case. So I'm going to change everything into x, okay? So what I get here is ds is going to be 1 plus of d. Yeah, 1 plus, yeah, dy, dx squared, and the dx, right? So you will get 1 plus dy, it's going to be 2x. Yeah, dy over dx. So now the integral becomes 2 pi, I is going to be x, ds is going to be this. X is from 1 to 2. This is the integral for that. I'm not going to waste time to evaluate integrals. Then you can use substitution to evaluate this integral, okay? Clear. Substitution works. Okay. Now, what happens if I want to decide to choose a y variable? That's okay. And you can check those two integrals give you the same value, okay? If you decide to choose a y variable, this is still, r still going to be x, okay? If you decide to use a y variable, okay, then y is still x squared, right? No problem. I is still x, okay? But ds is going to be dx over dy squared plus 1 over dy, right? All right, so in other words, x is going to be square root 1, okay? So now using the y variable, so you will get the derivative of x with respect to y is going to be this. Now, what is the domain for y? Domain for y is from 1 to 4, right? So this is going to be the integral, right? 2 pi. I is going to be x. So the x should be replaced by y, so square y. And then ds is going to be right, and the y is from 1 to 4. So you get quite different integral, but then they should be the same value, give the same value. Yeah, the second one, you still have to probably have to use a substitution to simplify the integral, but you can evaluate this integral. Right? So there are two integrals for the same surface area. It's not unique, right? Because they're all coming from the same integral. It's 2 pi r. Yes, it's neutral. No x, no y. You can use x value, you can use y value. Depends on which one you want to take it out. Right? Yes, remember, ds is going to be square of dx squared plus dy squared. You can take a dx out, you can take a dy out. Depends on the problem. But this x, this radius r, cannot be changed to y or to x. If it's x, it's just x. If it's y, it's y. Okay? So use that reason I have to change. You know, I can still put x here, but I have to change x to the y. The reason is this is the integral with respect to y. Okay? Similarly, here's the next problem. Okay? Find the area of the surface generated by locating the curve y equals e to the x. X is between 0 and 1 about the x-axis. Yeah. Again, I have to say that you have to understand the ideas to set up the integral. Otherwise, 50% of the students will get a wrong answer because I'm asking to, you know, they use yeah. If you know, if you don't know what's going on, just trying to pick up a formula from the book, and you even without drawing a picture, then it's harder to get a right answer. Okay, so here's a picture: y equals e to the x function, right? It's a similar picture here, right? So this is when x equals 0, y equals 1. When x equals 1, y is e. So if I ask you to draw the surface, okay, around the x-axis, then draw the surface along the axis. Don't draw the one along the y-axis. So read the question carefully. You get total different surface, right? If this is located about axis, that's the picture you get, right? Right. So what is dA? dS is going to be 2 pi r ds. Okay. I can tell whether you pay attention to my lectures or not. Because if you immediately put the integral and the square root of blah, 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 ds, that means you even didn't pay attention to my lecture. You just look at the formula in the book and put it there. Okay? If you write something like a 2 pi r ds, and I think you pay attention to my lecture. Okay? So, right, you take a point here. This should be original curve. Okay? Yes, when I was grading test quizzes, actually, you just put directions, put the integral without understanding where the and maybe 30% of the formula is wrong, you know. So you pick up a point on the original curve you use it to generate the surface, okay? And you draw the radius r. This is a part of the solution, okay? Don't focus on the answer. This is encouraged, not the elementary school, okay? So you have to show the idea step by step. You know, even the answer is wrong, you get 80% of credit, okay? So this is a picture, you have to show that. And then look at the picture, what do you have to write down? So, yeah. So first of all, you know, you can say area is going to be 2 pi r ds. Yeah, you don't need to write the first one, just write the second. But you have to tell me what is r for that particular point. R is going to be y, right? R depends on y. But y and x are not independent variable. Y and x are related. Y equals e to the x, and x equals natural log of y. So, you know, y equals e to the x equals natural log of y. So they're related. Okay? So essentially, it's just only one variable here. Okay? So then you decide which variable you're going to use. You can use the x variable, you can use y variable, doesn't matter. Okay. So dx, if you use the x variable, will be 1 plus dy over dx squared and dx, right? Then you evaluate, then you find the derivative, which is going to be e to the x squared and dx. Right? So this time you use x. So in this case, you have to change your y to e to the x. Y equals e to the x. Okay? Yeah. So now the area is going to be integral 2 pi. What is r? R is e to the x, and 1 plus e to the x squared and dx. X is start from 0 to 1. It's very clear. Then you start from the original. So don't just write down the formula there, then you'll be confused. Without the picture, I don't know how they figure out R. Okay? But you can also use the y variable. Then it will be dx over dy plus 1 and the dy. Right? Now this time I have to use the other relationship, x equals nature of the y. So it's going to be nature of the y was the derivative nature of y was respect y, so 1 over y. Right? All right. So the area is going to be 2 pi r. R is y, right? Remember, right? And this is going to be, you don't need to change the x, get dy. Now, what is the domain for the y variable? Look at the picture again. The picture clearly tells you the y variable is start from 1 to e, right? Okay? So from 1 to e. So this is another integral. The two different integrals, it's up to you which one you want to use. Okay? That gives you the same value. You can customize. Yeah, we go home, you just evaluate these two integrals. You will get the same answer. I'm not going to waste time to evaluate these integrals. Okay? I just want you to see how they are set up, the integral. Right? Yeah. So, but not always you can have two different integrals for the same surface area. The reason is, like here, I can solve for x. I can solve for x. I can express x as a function y and express y as a function x, just because this is increasing curve. Okay, if it's a parabola, I have no choice. Okay, here's a picture. Okay, find the surface area. Okay, so how do I get this? This is a parabola. Okay, y equals x times 2 minus x. Yeah, y equals x times 2 minus x. Okay, so this is a 2. So when you rotate, yeah, it's a rotation is about the x-axis. Okay, if you rotate about the x-axis, what do you get? You will get something like that, like a ball. Looks like a ball. Okay, so this is my picture. It's not a real ball. Okay, but it's if you find something like that, and you figure out that the year was like 10,000 years ago, and then what do you think? Right? So I saw something like that in South Africa underground, 300 meters deep underground. I saw some balls like that. Okay. And, yeah, so we don't know. Maybe there's certain civilization, some civilization. All right. So this is let's find a surface area. All right, so for this particular problem, original curve, pick up a point on original curve, right? With coordinate x and y. But this time, you can only express y equals x times 2x minus. If you want to express x as a function y, it's very complicated. So I'm not going to do that. Okay. So this is radius r. Okay. So the area is going to be 2 pi r ds. Then I look at this picture. Okay. I think I should use the x variable for the integral, not the y variable. Okay. So first of all, r is going to be y. Okay. That's okay. Y is going to be x 2 minus x. Then ds, I think I'm going to use the x variable, so it will be something like that. Okay? And then I differentiate, this will be 2x minus x squared. So when I differentiate, I get 2 minus 2x squared and dx. Good. Okay, everything now is in x and put into the formula. It's going to be integral, x is from 0 to 2 pi, I is 2 minus x, and ds is this. Okay, you may not be able to evaluate this integral, may be complicated, or it's okay. As long as you can set up this integral, you can always use software to evaluate. Okay, I estimate. Right? Right, so this is one. Now, I don't think, because you cannot express y in terms of x, so we're not going to do that. Okay. Yeah, so for this particular problem, you can only use x variable. So now let's look at a problem from the book. Find the surface area. And the surface is generated by locating the curve y equals 1 plus 4 to the x. X is between 0 and 1. This is going to be about the x-axis. So let's take a look at the picture. When x equals 0, this is going to be square root 2. When x increases, when x equals to 1, that's going to be, yeah, I think this will be the curve. Here is 1, square root 1 plus e. Okay? This is the 0 and the square root 2, right? Okay. So the rotation is about the x-axis. But since since the function is increasing function, since the function is increasing function, so you can express y as a function of x. You can also express y, the axis of a function y. So for an arbitrary point on this curve, right? Y equals the square, right? They're related. But you can also square both sides. Same like this, right? You can also change it to e to the x, yeah. X is going to be natural log of y squared minus 1. Right? So it's the same. But you have here x is between 0 and 1. I think here y is between square root 2 and square root 1 plus e. Right? Right. So we can set up a 2 integrals for the surface area. Okay? You know that the area is going to be integral 2 pi r ds. This is neutral formula, not with x. Yeah, I want to learn this because this is this you understand which variable you can use. Otherwise, you're confused. Why is this? Why is it? Why? Yeah, without drawing the picture. Yeah. So for example, even the axis even cannot be x-axis. Could be any horizontal line. Right. So let's write down. If we use the x variable, yeah, but r have no choice. R is going to be y. But if we use the x variable, that's going to be 1 plus e to the x, right? Okay. Then ds could be 1 plus dy over dx square, right? Dx. And the derivative of this is going to be, right? Yeah, you just differentiate it, that's what you get, okay? And then you're done. You get a formula, x is from 0 to 1, 2 pi r should be this, and then ds is going to be this. Right. Maybe you can simplify it. Yeah, but I'm not going to do it. So this is one of the integral. You can also use the y variable. In this case, you have to use other expression. X depends on y. And x depends on y. I think it's going to be y squared minus 1, 2y. I think, yeah. 2y, y squared minus 1, squared plus 1 dy. Okay, the derivative of x with respect to y. All right, so the formula may be, it's similar, right? It's going to be, a is going to be integral from this, and what is the ri is just y, that's fine, you don't need to make any changes, then the ds, and dy. And what is the domain for y variable? We're making square root 2 and the square root 2 and square root 1 plus e. All right, so you get two different integrals. It's possible, I just asked you to set up integrals for the surface area. You don't need to evaluate. All right. Now, for the same curve, if you draw the long picture, you end up with a complete different answers. For the same picture, for the same curve, right? This is the curve, right? Y equals square 1 plus e to the x, right? And this time I'm going to rotate about the y-axis. Yeah, location. Yeah, x is between 0 and the 1, because this is a rotation about the y-axis. So the surface is a different, completely different surface. Right. In the space, they're totally different surface. Now, you look at that, the other one is located about y-axis, right? And they match clearly. So I guess you have two wheels. One is, they're located. They probably always touch to each other. So that's nice design. Right? But then surface area will be different, completely different surface area. Right? Yeah. So here, right? How do you find the surface area? Right? Again, the same formula. This is a universal formula, 2 pi RDS, right? And then you can write down two formulas, two integral formulas, right? And I see x could be natural log of y squared minus 1. Here's a y between scale 2 and scale e plus 1, okay? So for the same curve, then you take a point x and y here. The only difference here is the radius r. The r is going to be x, not the y here, okay? But I think the ds is still the same ds, honestly. Still the same ds, right? So the only difference is, yeah, ds is going to be, let me copy what we got here. That one, okay? ds is going to be 1 plus e to the x, 2, okay? Or the other one is going to be 2y, y squared minus 1 squared plus 1 dy, okay? So ds is the same ds. The only difference is the r, right? Because the r could be x, but x can be natural log of y squared minus 1, okay? So now you just, it doesn't matter which variable you're going to use. You can use x variable, you can use y variable. Right? If you use x variable, just use the I equals x. If you use y variable, you have to let the r to be natural log of y squared minus 1. Okay? So the first one is going to be, let's use x. 2 pi x. Then use x. Okay? X is between 0 and 1. But if you use a y variable, and x is going to be natural log y squared minus 1. Then here inside, and this is almost impossible to evaluate, right? But you have two integrals for the same surface area, okay? But this part is always ds, this part is in r. Depends on which variable you can use for the length, okay? Or for this curve. Yeah, the curve can be described. Think about that, right? The curve can describe as arc length. But this curve can be also described using x variable. This curve can be described using y variable. Either way, yeah, you can use x variable for the curve. You can use the y variable for the curve, and you can also use another parameter to parameterize this curve, right? Yeah, let's find the area of the sphere, right? That's the one we learned in middle school, right? Do you still remember the area formula for the sphere? It was the radius r. Okay. So yeah, let's do this problem. Okay, this is the last problem, right? But the sphere can be, how do you generate a sphere? You can rotate any of the curves, right? The semicircle. Use a semicircle. If you rotate in x squared plus y squared equals r squared, you can rotate about the x-axis. Then you get the surface area of the sphere. So A equals 2 pi r ds, right? I'm going to write down the formulas. So if you use this is a point and this is radius r, right? So that's going to be, use the x variable. Use the x variable, then the y is going to be square root of r squared minus x squared, okay? So x is going to be y, I is going to be y. Right? And this will be dy dx square and dx. Okay? So y is the x varies from negative r to positive r. So I have to use this radical. 1 plus okay, x. Yeah, this is a formula, and you see that's pretty complicated, right? It's pretty complicated. Yeah, let's simplify a little bit, and then move it to this inside. You get r squared minus x squared, and here you canceled the plus x squared. Not too bad. Okay, what you get is x squared cancelled. So you get integral from negative to r, positive to r, and r dx. This is going to be 2 pi r times 2r, 4 pi r squared. That's the surface area of the sphere. Okay, and now we use a calculus to derive the formula. Okay, I don't think you can understand that when you're in middle school. Okay, you just accept the formula. Okay, so remember the sphere, for the sphere, right? With radius r, area is going to be 4 pi r squared. The volume is going to be 4 pi r divided by 3 r cubed, y divided by 3. Okay, but it's interesting. 4 pi r is going to be 2 pi r squared plus 2 pi r squared. It's going to be 4 times pi r squared, right? Pi r squared is the area that this. So the surface area of the sphere is 4 times the area of that disk in the middle. So that means our Earth, for example, what is the area, right? If you know the radius and you cut the Earth into half, that cross section, the disk, that area is going to be, right? The surface area of the sphere is 4 times the area of the cross section. Yeah. And then in mathematics, now we prove that, right? But if there's another way to understand, to prove this, okay? So that's it. I'm going to stop here, and there'll be no quiz Friday yet, but we're going to have a test very soon. Okay.